Hello students, we'll move on with the same concept that we discussed in the video 17, electric flux. Electric flux, a scalar quantity. Flux is a scalar quantity, a product of two vectors. And how did you define the electric flux? The electric flux is defined, flux generally electric flux phi E. Flux word is used with different physical quantities like water flux, electric flux, magnetic flux is given by the definition value of electric field into area into cosine of the angle between the area and electric field. As I explained to you yesterday in the video 17, we have to go through that thoroughly, understand all the concepts. There I introduced what is electric flux, how you have to find electric flux, why area is considered as a vector, what is its direction, and why A cos theta in the expression, not just A, and why EA is flux. All that I explained. Let me start my discussion with this expression, that is E into A into cos theta, and this also written as E dot A. This is dot product of two vector quantities, namely electric field and area. As it is a dot product, students, it is a scalar quantity, has only magnitude but no direction. That's the thing. And one more thing you can remember, phi E is also written EA cos theta, AE cos theta. So E into A cos theta is product of electric field into component of area in the direction of the field. Yesterday I explained you. Watch the video 17. Or you can write product of area into component of field in the direction of area. This is very important. Whenever we write this, you have a situation in your mind as I explained now. Once again, I will brief you how to think this relation. You have to think. Otherwise, these relations and discussions look very strange. You have to think it like this. What is the meaning of this? So students, in the entire region, there is electric force. Electric force acting on unit charge. Right? Let us suppose the electric field acting at this point. Not only here, entire region contains electric force. Means there is some charge here. Source charge I have not shown. Only influence can be felt. How do you feel influence? By placing a unit charge here that experiences force in this direction. This is the direction of force per unit charge, that is termed as field. Right? Whenever we write electric field, we don't write this term, but that is there. You have to think like that. Electric field. Not only here, everywhere in this region, we can see the direction of the field and value. Now, I imagine or consider a rectangular area of cross section, right? Rectangular area of cross section. This rectangular area, not exactly in this direction. Students, we assigned a direction for the area yesterday. What is direction of area? Look at this tile once again. See, you are looking at this surface. The other is this tile. The top and this is bottom surface of the tile. When you place it on a floor. See, you are looking at the top surface of the floor. What is direction of the area? Direction of area is this. What is this, friends? Normal. Normal to the area. When you are looking at this becomes the normal. When you are looking at this becomes the normal. If I fix my upward direction positive, if you look from above here, this is positive. Since you are fixing up for positive, down will be negative. Then you look at the area like this will be negative direction. Right? It depends on how you choose direction. That's the point. This is for one single surface, students. Now another case, to treat normal as a vectors. Look here, there is a box, cubical box. This is three-dimensional object, 3D object. If you consider only surface, 2D object, length and breadth. Look here, this is length and this is breadth. But here, length, breadth, height, three are there. Length, breadth, height, three-dimensional object. Here, always how many surfaces are there? 1, 2, 3, 4, 5, 6. When you are looking at the surface, this is the normal. When you are looking at the surface, this is the normal. This normal. Here, normal here, below, down. Right? If you look at this surface towards me, this is the normal. Means, when you consider a closed three-dimensional object, it is a closed three-dimensional object, then the normal is pointing outwards from the surface, outwards. ಇಲ್ಲಿ ನಾರ್ಮಲ್ ಔಟ್ಸೈಡ್ ಇರುತ್ತೆ ಯಾವಾಗಲೂ ಟು ದಿ ಸರ್ಫೇಸ್ ಇಟ್ ಈಸ್ ಔಟ್ಸೈಡ್ ಔಟ್ವರ್ಡ್ಸ್ ನಾರ್ಮಲ್ ಇಸ್ ನಾಟ್ ಇನ್ವರ್ಡ್ಸ್ ಯು ಆರ್ ಲುಕಿಂಗ್ ಇಂಟು ಬಟ್ ನಾರ್ಮಲ್ ಆಲ್ವೇಸ್ ಔಟ್ವರ್ಡ್ಸ್ ಬಟ್ ಇನ್ ದಿ ಕೇಸ್ ಆಫ್ ಟೈಲ್ಸ್ ಇಟ್ ಡಿಪೆಂಡ್ಸ್ ಆನ್ ದಿ ಸಿಚುವೇಶನ್ ಇಫ್ ಯು ಲುಕ್ ಅಟ್ ದಿಸ್ you may take this positive direction. If you consider this can be considered positive. But if you fix your direction upwards positive, in that case down negative. There are two options. But in this case, only one option. This is positive direction of the area. Normal. In the three-dimensional closed object, outward normal is considered, inward normal not considered. In the case of ball also, look here, this is a ball, right? So in this ball, when you are looking at this surface here, looking at this surface, this is the outward normal, and this direction is referred not into, it is out of this surface. That is referred as a direction to the surface at that point. Where is the surface? Here, a small benzene-like structure. That is the surface. To that, this is perpendicular and out of it. That is the direction of area. Right? Now, in this case, where is the direction of the area? This is direction of area. Approximately, this is the direction of normal direction. Normal to the area. Now, obviously, electric field makes an angle theta with the normal. How do you find the value of field in the direction of the area? That is E cos theta. What is E cos theta? Component of field in the direction of the area. For that, you draw perpendicular from the head of the vector E. And this vector E is considered hypotenuse. This is opposite side and this adjacent side. What is adjacent side? Adjacent side is hypotenuse into cos theta. This is the direction value of electric field along the normal. At an angle theta, electric field is E, but along the normal, the value is E cos theta. Therefore, at every point in the area, here the value of field along the normal, E cos theta here, E cos theta here, E cos theta, everywhere, the normal component is also called what? Normal component. This can be called normal component of field. Normal component of field into area, that is flux. Everywhere electric field is along the normal. So at one point value is E cos theta over the entire area into area. And I wrote SI unit. What is SI unit? Unit of electric field Newton per Coulomb into area meter squared. So it is Newton per Coulomb meter squared SI unit. This much you learned in the last class, right? Are you following? Now if you consider now electric field into the plane, you will get minus sign. Why minus? The electric field is opposite to the normal. When they are in the opposite direction, angle between them 180. What is cos 180? Cos 180 is minus 1. You get minus AE. If electric field and normal are along the same direction, electric field, this is the normal, see students, N, and electric field is in the same direction, E. As they are in the same direction, what is theta here? 0. What is cos 0? Cos 0 is plus 1. Therefore, electric flux is E into A. Now, if normal is up, like this, electric field is pointing down, E. What is the angle between them? 180. What is cos 180? Cos 180 is equal to minus 1. Therefore, the flux phi equals to minus E into A, where A is area and E is value of field at one point. Students, finally, what is flux? Flux, electric field over an area you consider, which direction? Along the normal. Can be called normal component of electric field over the entire area is called flux. It is given by A into E into cos theta. This is what you have to remember. Whenever I use the word flux, electric field over an area, what is it? Electric field value along the normal E cos theta into value of area you consider. Which area you consider? That you have to multiply. Right? Now it is time to practice writing expression for flux for a closed surface enclosing some charge. If it encloses charge, how to write electric flux? If it does not enclose charge, but the surface is inside a electric field, how to write electric flux expression? This one we will practice. It will be very useful for our next topic, that is application of Gauss theorem. And writing electric flux expression for different cases is there in your NCERT textbook. So it is normally covered in CET and NEET examinations. That's why you have to practice writing expression for electric flux. Under that, I have one case, flux through a spherical surface with charge at the center. See, this is a spherical surface. Spherical surface like this ball. I have cut this ball for other purpose here. I have placed a charge inside exactly at the center. If you don't place it at the center, will not be any flux? Yes, there will be flux. If charge is anywhere inside, there will be flux out of the surface. Flux means what? Electric field influence all around the surface. You need not place charge exactly at the center, but for simplicity, what we call symmetry. Symmetry is an important word in physics. Using that, we simplify problems of physics to a greater extent. Right? One of such examples of symmetry is this. What do you mean by symmetry? First of all, you understand the scenario, situation. What is that? There is a sphere, like the ball I showed, and a charge at the center. Now the charge is at the same distance from this point here and also this point, right? And one more point here and another point here. Point here and a point here. Means if I draw a line like this, which passes through the center, what do you call this? Popularly known as what? Diameter, right? Every point to the right has a corresponding point in the left. See, every point on the right side of the circle has a corresponding point on the left side. Symmetry. So this is mirror image of this. Symmetry, very important concept. Now the point is very simple. What are you doing? You are finding electric flux through a spherical surface. That much we see now. There are a lot of things to be learned, discussed here. Let us suppose there is a point, unit charge. When we place unit charge will be repelled by this positive charge towards up. Electric field is E. If you consider a point here also the electric field is to the right, means a unit charge is repelled right. Here it is down, electric field is acting down. To the left, the electric field is acting to the left. Everywhere you can write any number of points. All around the electric field is acting along the radial direction. What is radius? Distance between this and any point on the surface. If you extend that line, that is the radius. One more point to remember, students. If we extend radius, we have learnt in our high school days with sphere, one of the familiar objects. We have learnt in high school geometry. So to this portion of the surface, the angle between the extended radius and the surface is 90. Very good. So this is 90 here. Now I want to find the electric field over this area. I consider a small area of cross section around the point. Right? This is what you need to do first of all to evaluate flux over the entire surface. You consider a small cross section. Surface area, let us write S. S for surface area of the surface. Very small, how you denote? Mathematically, differentiation, derivatives, ds, very small area. So it has a direction. What is the direction? S. Direction is along the normal. I write here using ping. The direction is along the normal. This is the direction of n, area vector. Electric field also in the same direction, students. If they are in the same direction, what is theta? 0. What is cos 0? 1. Therefore, electric flux is just E into A. What is flux here? Flux through the surface. If I write d phi 1 at this point, what is d phi 1? It is electric field value E and area ds into cos 0 degree. Why? They are in the same direction. Therefore, the value is E into ds. Now, if you come to this, here also electric field is E. Now outwards. You consider area of cross section, right? You can do the same for all areas all around. Here also the same area. Here also same area. Here also same area. Area of cross section ds. ds is pointing outwards, right? Pointing outwards. This is also area ds pointing outwards, right? Here also area pointing outwards, and the area size ds pointing outwards. All around the electric field is pointing along the normal. Therefore, here also electric flux, if I write E d phi 2 equals to E into ds, that's it. You are not writing electric field here E1, here E2, here E3, here E4, here E5. Why? Because I am writing the value of field. What is value of field? Value of field due to a point charge. I'll remove this part now. I'll come to next one. See, what is value of electric field? Value of field E equals to 1 over 4 pi epsilon 0 charge Q divided by R square. Charge Q same for all the points on the surface, and distance radius is same, right? That's why Q and R square same for all the points on the surface. Electric field is same. That's why flux here ds d phi E into ds. Here E into ds, here E into ds, here E, everywhere electric flux is, if I consider dE4, that is E into ds. Here electric flux d phi 3, that is E into ds, and so on. Everywhere electric flux is what? E into ds, which is electric field is along the normal. Electric flux is a scalar quantity, is not a vector. Since it is a vector, how do you add? Just add like a number, right? So, students, one point you have to remember, the flux in this example, in my explanation, here in this case, electric flux through the area. Which area? Area very small ds. I gave the reason why D is used, S is used. S for surface area. First letter of surface area S. S area. And D very small. For a small area, the electric flux d phi equals to E into ds. Right? Then total flux over the entire area, total flux over the entire area, very simple, students. I write phi. What is the symbol? This is read as phi, phi, one of Greek alphabets used for electric flux, symbol for electric flux. If I write E, electric flux, B, magnetic flux, and so on, generally flux, equals to, what is that? Electric field EDS, and you add over the entire surface areas. What is the meaning of this? Once again, you visualize it like this. See, two hemispheres. I put charge at the center, right? Then I close. Now there is flux coming out, right? Flux coming out, like light coming out of a glass bowl. If the bulb is inside, there are patches, right? Patches here. Each patch has a area ds. Then electric field is along the normal. What is electric flux over a small area? ds, E into ds. One patch EDS. Two patches, 2 EDS. Three patches, 3 EDS. Four patches, 4 EDS, and so on. We will complete adding till you complete the what? Patches. So, adding process is is stated this way. You are adding EDS over the entire surface, that is summation EDS. Here electric field is a constant, right? It's not varying. That's why you take field outside, then it is summation ds. You are just adding what? Areas. Everywhere electric field is E. That's why ds, 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 all ds you are adding. ds plus ds plus ds plus ds plus. Like, you consider it as a football. You cut all the patches, separate them. Then you start stitching, right? When you start stitching and complete, it becomes what? The sphere. Therefore, the total area is sum of the areas of all the patches. Therefore, the term summation ds is total surface area. You know what is total surface area of sphere? Can you write? Yes. What is surface area sphere? 4 pi r square. Therefore, the value of flux E into 4 pi r square. This is flux expression, right? Students, always flux is electric field into area. What is the type of area? Sphere, 4 pi r square. If it is curved surface of a cylinder, curved surface of a cylinder, then it is 2 pi RL, 2 pi RL into E. If you consider a square plate like this, what is area? Length into breadth. A square. So, electric field into A square. If you consider a circle, electric field into area. What is area? Just pi r square. Like that, for different surface areas, different term appears here with electric field. Very simple. This is how you find. We did this in the last video, last section. Last video 17, this is video 18. 17, last section, we learnt electric flux, students. Right? Now we are one step away to arrive at famous Gauss theorem. I wrote that also. What is electric flux expression? See here, electric flux expression, use that here for this. So phi equals to flux is 1 over 4 pi epsilon 0, charge q divided by r square into 4 pi r square. 4 pi r square cancels, you are left with 1 over epsilon 0 into charge enclosed. Therefore, electric flux phi equals to 1 by epsilon times, epsilon 0 times the charge enclosed. If the medium changes, instead of epsilon 0, epsilon is written. For different media, different values this. Q is charge. How do you state this? Left side is total electric flux through the entire surface. What is the surface? Spherical. That's equal to 1 by epsilon 0 times the charge enclosed. Famous Gauss theorem. How do you state? Total electric flux equals to 1 by epsilon 0 times charge enclosed. I wrote in the last video, last section of my discussion, last part of my discussion. We will state once again before we come to application of Gauss theorem. But I explained you how to evaluate flux over a given surface area. Students, there will be net flux when charge is enclosed by the surface. That's one thing you have to remember. Now another question arises in your mind at this stage. What if charge is at some point here, not at the center? Then also you arrive at the same expression for flux. Only thing is the value of field here different. This nearest point, this is farthest point. Field minimum, field maximum. So in these expressions you cannot write just EDS, even DS. E2 ds, E3 ds, E4 ds, E5 ds. You add all the values of electric fields, right? Write expression for electric fields here, then you add. There is an important branch of mathematics called integration that takes care of addition. You have not come to that as till now. You will learn that this year. You need not bother about that. We have considered only symmetrical case, simplest of the cases. As you learn more and more mathematics, more and more complex problems in physics taken, right? Here very simple. Charge is at the center, all the points are equidistant, electric field is same. That is 1 over 4 pi epsilon 0 q divided by r square, right? This is how we apply. First you learn this, then you will think of complex situations. When there is charge, there will be flux outwards, natural, right? If you consider it as a bowl, glass bowl, you put a source of light, LED bulb inside, then there will be light, right? If you don't put a source of light here inside, then there will be no light coming out of it. But if you hold it against this source of light, light enters here and passes through it, right? Amount of light entering equals amount of light passing out, right? Therefore, flux in equals to flux out. Incoming flux equals outgoing flux. Total flux is 0. That situation we will see now with electric field also. This is one case, student. To find electric field, electric flux through a spherical surface with charge at its center. So very simple thing. You write this diagram and write this part of the explanation in your notes, page number 14, 15, 16, reserved for empty pages are there, reserved for this part of writing. This normally least asked in board examination. So that's why I am not given in the notes. In my regular class, I ask you to write down in the notes or notebook. Practice it, that's it, right? You now watch this video, write this diagram and write the explanation. Remember how we analyze flux, how to find flux. If you practice, that's enough, right? That will be useful, especially CET NEET classes. Otherwise, you think, oh, this has not been taught, like that you think. I have told you how to evaluate flux. It is oftenly covered in NEET and CET examinations. I will show you the examples, right? Board examination, very simple. State and explain Gauss Theorem. I have explained, stated. Then 3 applications. We will practice, no problem, right? This is what we have to remember. For flux through a spherical surface. Next one as I told you, when there is no charge, how to find flux? One example is given in our NCERT book. I will take up that. Is there in our NCERT book. I will show. The second case is flux through a cylinder, placed in uniform electric field, in a unifier right here, in a uniform electric field with its axis parallel. I write here parallel like this, parallel to the field. There is a uniform electric field. You have placed a cylinder, you know, right? Cylindrical surface, very familiar to you. I'll remove this part. Okay. Now, what is electric field? Again, force per unit charge. How do you produce uniform field? Like this, if you consider a charge surface, there will be charge arrangement over a surface charge distribution like this. And this charge distribution producing electric field all around uniformly. Students, you know, as you move away, electric field decreases. But let us suppose, for simplicity, electric field is like this. Here it is like this. Value of field is E. Here also field is like this. Value of field E. Here also value of field like this. So uniform field. How do you write uniform field? By writing arrows parallel to one another, equidistant, parallel to one another. That is what? Uniform field. Now let's consider cylindrical cross section. How? The condition is it should be parallel to the field. Field is to the right. So I consider a cylinder. This is one end face of the cylinder. This is the other end face. I write like this. Both the ends visible like this. Right? See, the electric field is just parallel to the longer side, right? This curved surface. This is curved part of this. This is flat and this also flat. Flat ends, curved part, right? Now, you have to evaluate flux. As I told the students, this is a solid three-dimensional object, right? Like this box, right? If you look at this box here, normal is towards me. If I look at the box here, normal is towards me. Like that, At this point, what is the direction of the normal? Here normal direction is to the right, n. See students, normal and electric field are in the same direction. What is theta for that? Theta is S, theta here equals to S 0 degree. Why? Electric field and normal are in the same direction. If you come to this surface, come over here, this is normal direction. Always normal is pointing outwards from this surface, perpendicular. Here, as electric field is into the surface and normal is out, electric field is into and normal is out. What is the angle between these two? Theta is what? 180 degree. Keep this in mind, students. One more point, you consider a surface cross section here over this curved part. So what is direction of field? S, direction of field here is to the right. Very good. And what is the normal direction? Normal direction, look here, normal direction is this, to this area, normal is up. You are looking like this area, n. What is the angle between these two? 90. Right? And this applies for all other points. Here also normal perpendicular to electric field. Here also normal perpendicular to electric field. Everywhere the normal is perpendicular to the electric field. Now we have to evaluate the flux. Let us divide the flux into three parts. Flux phi 1 through the end phase parallel to the field. This end phase opposite to the field. And the curved part. Now let us find flux number 1, case 1, flux through end phase. Let us name end phase A. This is end phase B, end phase A. See A, here is the diagram. You write this in your notes. Page number maybe 11, 12, there is an empty space. Write this. Just keep in mind, this is how we have to write expression for flux. Very important for CET NET. Different cases will be taken up, I will see. What is flux? Flux is again, see here students, the end phase area. What is area? Let A, area of end phase, and E, electric field value. Then what is flux phi 1? Phi 1 is electric field value A, E, electric field value E into area A into cos. What is the angle here? 0. Why 0, students? Again, electric field is in the same direction as the normal. What is the total value? Plus EA, right? Plus EA. This is the value. Now come to the case 2. It's very interesting. It's very easy to follow. And flux through end phase B. What is flux through end phase B? Again, you write that phi 2. For that also area A, electric field E. What do you write? E into A into cos 180. Why 180, students? Again, the direction of area is to the left, electric field is to the right. What is the angle between them? 180. What is cos 180? Minus 1. So it is minus E into A. That is flux. Third one, case 3. Flux through curved part of the cylinder. So curved part of the cylinder. What is angle theta? Theta is 90. Now I consider one small area say ds, right? At this point, what is flux? Total flux phi 3 is summation of electric field into ds into cos 90. What is electric field? A cos theta. A is ds, very small area. I consider this curved part made up of large number of small areas. Look here, like this, a cylinder. So over this surface, I consider a small surface ds. Here normal is perpendicular, electric field is horizontal. What is angle? 90. Now you need not bother about the summation. This third term itself is 0. So if you multiply 0 with any quantity which is non-zero, total product will be 0. So E into ds into 0. 0 multiplied by anything is 0. Total value is 0. Therefore, what is total flux? Therefore, total flux as flux is a scalar quantity, phi equals to phi 1 plus phi 2 plus phi 3. What is phi 1? See there, plus E into A. What is phi 2? Minus E into A. What is phi 3? 0. So, plus EA minus A again, same opposite side, 0. Implies net flux. How do you read this? Net flux 0. Not flux 0, net flux 0. What is the meaning of this? Whatever the flux that enters will leave. Whatever that enters will leave. Like this. The light that is entering this hemisphere from that direction will be leaving this away. So there is no extra light adding with this, or there is no loss of light. Net flux 0 y, whatever that enters will leave. Like that, whatever the field that enters here will leave here. That's why net flux is 0. What is the conclusion? No charge enclosed by the surface, no net flux. Very important observation. One more question. When is flux 0? I will give some questions. You have to answer them. When is flux 0? Flux is 0 when the charge enclosed by the surface is 0. Flux 0, charge 0 enclosed by surface. Net flux is 0. You have to say net flux. Whatever the flux that enters will leave. That's it. Flux means electric field over the entire surface area here will be equal to electric field over the surface area here. It's like coming in, it's like going out. That's why total value is 0. This is what you have to remember. This is the case in uniform field. Very, very important. Field value here different, then the sum will not be 0. This will be more, this will be less, and the difference will be negative. This term will be more, this term will be less, because this is nearest to the charge distribution, this surface, this bit away from the charge distribution. That's why this will be more, this will be less, like that it will be. But here, as the field is uniform, total value here, same, difference 0. Important point is there in your ncert book, right? He has covered these two, electric flux through a curved spherical surface and also cylinder. In spherical surface there is a charge inside, there is net outward flux. Here there is no charge inside, electric field is entering from outside, whatever that enters will leave. How we find flux, all that will be a practice. We just know how to apply flux, that's it, that's enough. You just recall it once again. So electric field is to the right, everywhere it is uniform. How do you show uniform field? By writing equidistant parallel lines, that's it. There is a cylinder, right, parallel to the axis is parallel to the field. One end B having area A, end A also having area A. This is curved surface. Now what is flux? Flux is electric field into area. To the surface A, you apply flux formula. Electric field into area. Electric field and area are in the same direction. Angle is 0, so E into A. Flux through the end face B, there electric field EA cos 180. Why 180? Because at this point, area is direction left and electric field right. Area direction left, electric field right. Angle between them 180. What is cos 180? Minus 1 minus EA. The third case, electric field over the curved part. You think like this, curved part, this curved part. So, is a large area, that's why it divide that into smaller areas, smaller pieces. You find flux through E small and then add. That's how we did in the previous example, sphere. You are trying to do that, but you analyze for one surface like this, ds, normal is up, field is right. What is the angle between them? 90. What is the expression for field? Flux, electric field into area into cos theta. whenever you have cos theta in the expression, check for the angle. If the angle is 90, then the total term will be 0. Don't bother about other things. The other quantities are electric field and area. The third term cos theta 0. Why? Because theta is 90. Therefore, flux is 0. So, flux phi 1 EA, phi 2 minus EA, phi 3 0. If you add all of them, phi 1 plus phi 2 plus phi 3, EA minus EA 0, total value 0. What is the conclusion? Net flux is 0 whenever no charge is enclosed by the what? Surface. This is a cylindrical surface. If there is no charge inside, there is no flux. That's one thing you have to remember, right? This is how you practice writing flux expression. And if you solve that flux expression completely, you will get an expression 1 by epsilon 0 into Q. That's what I showed with spherical surface. Flux equals to, for all situations, when charge is enclosed by the surface, whatever be the shape. See, this is cubicle. In a cubicle box, you put some charge inside, flux through the entire surface areas. There are 6 faces. Entire surface area, 6 times the area of each, right? If you find flux through entire surface area, that will be equal to 1 by epsilon 0 times the charge enclosed. That is statement of Gauss theorem, right? Gauss theorem, and we are going to apply Gauss theorem for different cases, and the same application will be used. Whatever we did, will be using to apply Gauss theorem for what? Finding electric field due to a continuous charge distribution. You know, expression for. Okay students, so far I explained you about the calculation of electric flux in two cases. One, over the spherical surface is there in the NCERT book. Same calculation part I discussed. Symbols may be slightly different. I used ds here, delta s, same surface. The other one, surface which does not enclose the charge, cylindrical in an external uniform field. That's also there in the textbooks here. Whatever I discussed are in the NCERT books, right? Normally these, as it is not covered in board examination, that's why most of the students here in our state don't concentrate on these things. They are very happy with the 5 marks derivations. There are some expected 5 marks derivations, 3 marks, 2 marks and 1 mark questions. You can expect questions. There will be choices and also problems can be expected. Similar types can be solved. You'll be happy with that. Many even don't look at the textbook. For those, CET NEET exam becomes very difficult. You don't do that. You understand whatever is there in the textbooks. Here, I explained this. You go through my videos once again. And I told you to write down these 2 explanation parts in the empty pages of my study material given to you. That is page number 14, 15. Now I will come to very important point I explained you. I explained you already. But let us see what he says in your NCERT book. Look here. These are important points. Many a times have been used to frame CET NEET questions. Let us see the points. There are 6 points, one by one, with a detailed explanation, so that we will be very much aware of the concepts discussed here as far as Gauss law and electric flux is concerned. Right, students? Let's read the first question, first point. What is the first point? In first point, it says Gauss law is true for any closed surface, no matter, I will underline the line, no matter what its shape or size is. What its shape or size is. Look here. No matter what its shape or size is. What is Gauss law? Gauss law is total electric flux phi equals to 1 by epsilon 0 times the charge enclosed. This what? We discussed in last class. Spherical surface, charge inside. Now to evaluate flux over the surface, we used a spherical surface which has symmetry. Symmetry means what? if I cut this, right side part will be a mirror image of left side part. And all the points on the surface are at the same distance. I explained you. This is symmetry. For different geometrical shapes, different symmetries can be applied. Very useful symmetry concept. Is there in the next point. That also. Now the point is, instead of the spherical surface, you consider another surface somewhat like this, an irregular shape. Can I find the flux over this and again use this formula? Yes, that's what he says. Calculation part of flux over this irregular surface is complex. We have to use complex mathematical analysis like integration. You will learn this year towards the end. Calculation part is complex, not easily done as easily as sphere, but this formula applies. That's what is his point. So what do you understand now, students? Whether the surface is regular like a sphere or irregular like the yellow surface here boundary enclosing the charge, Gauss law is applicable. First point. Remember this. It could be a one mass question. This point could be a one mass question. Can we use irregular surface to evaluate flux and apply Gauss theorem? Yes. Answer is yes. Sometimes used in setting CET questions. You will see how CET questions have been framed on these points in our MTG material. I will show you. Next one. The point is the term Q on the right side of the Gauss law includes sum of all the charges enclosed by the surface. Charges may be located anywhere inside. Look here. I consider this as a point charge Q in my discussion, right? What he says, Q is not a single charge, it's a collection of charges. Those charges can be anywhere inside. One charge can be in here, Q1. Other charge can be here, Q2. Third charge, Q3. Like this, discrete charges. But they are separate charges. There is clear separation between the charges. But all of them have been enclosed. Now, you write this relation. Flux phi equals to, same relation I am writing here. What is that? 1 by epsilon 0, charge enclosed. You can write capital Q or small q, ENC. What is ENC? Enclosed charge. What is that? Sum of the charges Q1 plus Q2 plus Q3 plus Q4. If one of them is negative, write negative. Get subtracted. That's it. Total charge. Maybe positive, negative. All positive. Flux emerges out. Outward flux you see. All charges negative, inward flux. Some positive, some negative. Depending on the sum, flux will be outwards. If net charge is positive, flux will be inwards if net charge is negative. Like that you think. That's what he says in the second point. Students, you have to remember all these things. Then only your CET NEET performance will be good. Right? Simply not. If you just prepare, why, define, explain, derive, that much you remember. That's how you have been trained here, right from the high school days. Your performance in CET NEET will be bit low. I am doing that, right? I am preparing you for the board examination, giving a precise notes. In addition to that, I am showing you what is there in the textbook. You have to think like this only. Think like this only. Otherwise, you can never improve performance in your CET NEET. Remember, you should read textbook after reading my notes and listening my video class. Now, you have understood first point, second point. What is first point? Gauss law, surface, while applying Gaussian surface, using Gaussian surface, it can be of any shape, like regular, sphere, cylinder, or irregular surface like this. And the right side term, charge, is a collection of charges, not a single charge. The charges can be anywhere inside, right? Anywhere inside, need not be at the center. Second point. What is the third point? Third point is a bit lengthy. Let's read that. Then I'll write the diagram to explain you easily. In a situation when surface is so chosen that there are some charges inside and some charges outside, the electric flux in bracket, whose flux appears on the left side, is due to all charges both inside and outside. All charges both due to inside and outside charges. The term Q on the right side of the Gauss law, however, represents only total charge inside. Look here, students. I'll remove this yellow. Yellow part is over that explanation. Now I consider this point. What he says in the fourth one, there are 4 charges in the expression in this diagram inside the Gaussian surface. This is Gaussian surface. What he says, you consider one more charge, say Q5 charge, one more. Now if you find flux over this region, the electric flux due to all the 4 charges, this and also this. So left side expression is total flux due to charges inside, charges outside. Not here, charges both inside and charges outside. Flux due to all the charges. But the right side term, total charge expression, should contain only charges inside the surface. Only inside charges must be considered. Outside must not be considered. Because if you consider entire surface and evaluate flux due to all the charges, here whatever the flux that enters will leave. If you add entering, subtract leaving, total term becomes ineffective due to this. Right? So left side flux due to all the charges considered, both inside, outside. But when you are writing the right side term, enclosed charge, only charges inside the sphere must be considered, not outside. You should not consider this point. Remember this. As it is, you think and remember. Very, very important, students. Next, we will go to the next page. What it says, 3 more points. The first point there on the top, look here. The first point is, let me read that point, then we'll come to this diagram. The surface that we choose for the application of Gauss law is called Gaussian surface. This line, as it is an answer for 1 mass question. What is a Gaussian surface? What is a Gaussian surface? What is your answer? The surface which is chosen to apply Gauss law, which encloses a charge. We can add one more word, which encloses a charge. I have given in my study material. See that is there. The same word, but one term extra. The surface that we choose for application of Gauss law, how it is, which encloses an amount of charges, is called Gaussian surface. Now, next he says, you may choose any Gaussian surface like this. Right? Sphere, irregular surface, cylinder, and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. Discrete means separate charges. You should not allow the Gauss law, a Gaussian surface, to pass through any of the charges. Right? If you allow, what happens? This is because electric field due to a system of discrete charges is not well defined. Where? At the location of any charge. As you go close to the charge, the field grows without any bound. However, the Gaussian surface can pass through a continuous charge distribution. This application we will see next using this idea. By considering Gaussian law, Gaussian surface passing through a continuous charge on a straight line, wire on a surface, we will see, right? This last line, there are 3 applications, right? We will understand that. But what about these 1, 2, 3, 4, 5, 6 lines meaning? I will explain you here. You read this line once again, then you understand this explanation. This is what he says. Students, I have written the Gaussian surface which encloses an amount of charges, right? He says, students, don't allow another charge Q5 to sit over the surface. If you allow charge to sit over the Gaussian surface, or if you choose Gaussian surface such that passes through the 5th charge, then you cannot apply Gauss law. Why? Because as you approach the charge, here to find the flux, what happens? As you approach the charge, means when you are very close to the charge, you are over the charge, implies distance becomes 0. You know, electric field due to that charge very close to is inversely proportional to square of distance. What is value when distance 0? 1 by 0 square. 0 square is 0. What is 1 by 0? Infinity, not defined. So electric field at this point not defined. You cannot include that. That's why don't allow Gaussian surface to pass through a charge, pass through discrete charge, right? That is the point. You understand this? Very, very important. Now the next point is the last but one. Say, I'll bring here. I'll remove this. See, the fifth point, Gauss law is often useful towards a much easier calculation of electric field when system has some symmetry. Some symmetry means what? Like this sphere, cylinder, right? If you consider surface, Gaussian surface such that it has symmetry like sphere or cylinder, your calculation becomes very easy. That's what we will be doing in next section, application of Gauss law. You will know that. What is telling this? What is the meaning of this sentence, students? We use symmetrical surfaces like sphere, cylinder, etc. Then problem becomes easy. Now the last point, also very important. Finally, the Gauss law is based on inverse square law dependence on distance contained in Coulomb's law. Right, students? That's what we did. Using Coulomb's law, we arrived at Gauss law and vice versa, right? Using Gauss law, you can reach Coulomb's law. Using Coulomb's law, you can reach Gauss law. That's why they are interrelated. Both are same actually. Any violation of Gauss law will indicate departure from inverse square law. If Gauss law is false, inverse square law is also false. Coulomb's inverse square law. That's why both are same. You think like this. This also could be 1 mark question. The same sentence, right? Explain why, like that they add and use this sentence only to frame 1 mark question. Like this you need to know, and based on the concepts you learned here, concepts you learned in these points, CET questions normally frame. You will see such questions in our MTG material. I will show you, students. That's why I am stressing you, telling you again and again. Sometimes you may feel, oh, he gives more explanation. Is it there in the textbook? No. Yes, everything is there in the NCERT book. You have to think like how I explain you. Then only your performance will be good. Preparing for the exam, board exam is a matter of 1 month. You will do towards the end. You understand all these things, right? We have given you precise study material. If you read that much, you will score 70 out of 70 in board examination. But I don't give you guarantee in CET examination. You are now learning subject, learn all this. What do you lose? No, you have time. Whole day you can sit and prepare all these things. Do this. That's what we and your parents expect you to, right? What do you do at home? Your parents investing on you, right? For your future. Do this. We will meet you in next class.